I'm Saran Kumar. I'm from Vijayawada. Let me introduce myself. I'm working in Capgemini as a physical design engineer for the past 3.5 years. Today, I would like to explain about the synthesis and the PNR flow in the VLSI domain. So, starting from the synthesis, we have two types of synthesis. One is a logic synthesis, and another one is a physical level synthesis. So coming to the logic synthesis flow. So it is the flow in this, these are the following the stages. Like in the first stage, it is the importing input files. And the second stage, elaboration, read SDC. The third stage, sanity checks. And the fourth one is generic mapping, technology mapping, optimization, DFT, incremental optimization, and generating outputs. So these are the stages which comes under in the logic synthesis flow. We'll discuss one by one in the each stage. So first of all, we have to take the inputs. So in the logic synthesis, we'll give these three as the major inputs. One is RTL file, which is nothing but Verilog file, which comes from the front-end team. And it is a timing library, which will be given by the vendor. And this is the synthesis team, like SDC, constraints team, will be provided by this SDC file. And so coming to the next stage, sanity checks. So once after receiving all the inputs, we have to check on the input files, whether is having any errors or any issues according to that input files. So it is categorized into three stages. One is a design or netlist checks, and another one is a SDC checks, and another one is a library checks. So coming to the first one, design checks. If you want to check for the design checks, we have to use this command, check underscore design. So under this command, we'll report if any of these below steps have been reported in this after giving the command, we have to report it to the front end team because we have to further proceed if we see through these issues. So it will cause an big errors or any flaws in the further PNR flow. So after giving the check underscore design, what under lot we will check means we'll check for the first one is floating pins. In general, in our design, if the standard cells have any pins, means those pins have to be connection. If the pins will not be connected, means that will be in the floating stage. If the tool wants to optimize in further in any one of the stage, the tool won't optimize on those particular cells because those pins are in floating stage. So it will cause errors in that time. Okay. And next one is multi-driven nets. If in our design, if any net is being there means it should be driven by only single cell or like that. It should not be driven by driven nets like multi nets should not be driven to any cell, else it won't capture any data properly. And the next one is undriven input ports. So in our design, we have input ports and output ports as well. So whatever the input ports we have in our design, it should be drive some load at least. Okay. So if not means that input which they getting the logic to that input port, it won't be propagated to the cells or any connected to the design. As well, next one is unloaded outputs. So unloaded outputs means the output port which were there, so it should be connected to that output ports. So if not means that port will be in the floating stage. So that that data won't be get into that output port and it won't be transferred to the and it the same port may be act as an input port to the next block. So it won't propagate that data also. And the next thing we have to check is unconstrained pins. So unconstrained pins means what are the pins in the design of the cells? I should be have some constraints on that timing constraints wise. Likewise, it has to be mentioned. If not, we have to report that one. And we have to make sure there is no combinational loops in our design. Combinational loops means if we have any logic circuit, let's say, in that logic circuit, if one input is given to the one cell, that output will become as an output Y. The same output be connected back to the input means that will be the loop. So these kind of combination loop should not be present in our design. And the next one is empty modules. So empty modules is nothing but in a we can call it as in a black box also. So in that module, it will have like some port information or any some hierarchic information, but in depth it won't have any connections wise. So it will be treated as an empty modules. And the next one is pin mismatch. So what pin mismatch means in sometimes in a design they have input pins and output pins and some are input and output pins. So in some cases whenever any input pin should act as an output pin or else vice versa in that case, if it not acting properly means that will be triggered as an issue, a design failure issue. And last one is cell or instances without IO pins or ports, etc. So the cell are which we call as instances. So it should have some pins or ports. If it is not having any IO pins or ports, it not be connected means that is also one of the issue in the design checks. So these are all the checks which we do in the design category or the netlist checks. So coming to the next stage, SDC checks. So to check for the SDC, we use the command check underscore timing. So upon giving this command, what and all checks we have to do, like what we need to report means there will be unconstrained paths. Since it is related to constraint means we have to check that any path is applying constraints like timing wise or delay wise, whether it is applying properly or not, we have to check that those paths. And it checks whether the clock is reaching to all the clock pin of the flip-flop. So you have to check what are all the flops in our design it is having. So the clock should be reached to all the clock pins of the in all the flops to the all the flops in our design. So it will check in this command. And the next one is check unconstrained endpoints. So any endpoints are there. So that those endpoints have to be unconstrained means like we have to give some delay constraints on that particular endpoints. Like if any ports have been missing any input external delay or any output external delay, it will be triggered as a timing issue. And the next one is if any port is missing sleeve or load constraints, means that also we have to report in the check underscore timing category, which means like if it is not driving any load properly or it is not to the expectation as the result. Likewise means we have to report this as a check underscore timing. And the last one is library checks. For this, we have to give the command check underscore library. For this, what it will do means it checks the consistency between logical and physical libraries. So when we providing with these two libraries, so it checks whether these two libraries have been consistently or not, any like syntax errors or any issue or any errors. Likewise, it will report. It checks the qualities of both libraries and it shows the number of cells missing, the number of metal or pins missing in the physical and logical library, which means if any like in any library like in physical or logical library, if any cell information or any pin information or any related metal information has been missing means that will be comes under the library checks with the help of this command. We have to report it according to the front end team and all. We have to correct it by this one. Is it my voice is audible? Hello?
Audible, sir.
Yeah, okay. So moving to the next stage, it is elaborate. So in this elaborate stage, it will have some steps. These are the steps. One is data structure, and another one is inference registers, and another one is HDL optimization. So in elaboration stage, what it does means in this step, data structure, if we are giving number of input files to the tool. So what it will do means it will take into as a single netlist file and it again it will read all those files and it will checks for the syntax and under it will takes all the input files into a single input file. Likewise, in this step it will do. And coming to the inference registers, what we'll do in this step, it means like if whatever the files which we provided to the tool, it will read and it will load those files and information it will be loaded into the tool. And in this step, whenever the tool reads any passage or negate in the input file which we provided, let's say RTL file, so it will treat it as a flip-flop. Okay, this is the flip-flop which I'm seeing passage or negate. And if the tool is seeing some if else statements of if else commands means that will be turned it as a marks. So it will turn the if else commands wherever the if else commands will be read in that file. So it will be turned it as a tool will identify, okay, this is the marks have to be likewise, it will infer. And similarly, any case statements are will be read means that will be taken as a priority encoders. And the next step in the elaboration stage is HDL optimization. So in this optimization, what it will do means any dead codes or any unloaded outputs or let's say any combinational loops, as we discussed earlier in Sandy checks, if it still it reports any thing here means it will check for that in this stage in the HDL optimization. So tool will remove all these things in the HDL optimization stage. So moving to the next stage. So in the next stage, it is the actually sorry. 1 second, the screen. Okay, this is the generic mapping, and here is DRV setting. Yeah, okay. So here what it do means read SDC. So in this command, what it do means, what the tool will do, whatever the input files which we given. So the constraints mainly, let's say in the SDC file, max strength, max gap, and max fan out, and a max length, and all the timing related models like wire length model and all will be information will be present in the SDC file. So those files will be read here in this stage, and according to that, that constraints will be applied really into the design. And next stage is generic mapping. So in generic mapping, the tool, what it will do means, here the tool converts RTL code into the symbolic gate level netlist, which means it is in a generic gates, which it don't have any technology related wise. And so it is a basic a kind of generic gates, which we can say it is a normal to the any design. So here tool is independent of technology. It won't map to the any technology. Just it converts the RTL code into a gate level netlist as we discussed earlier. If any if else statements has been read means it will be turned as an marks. Likewise, it will be mapped into the generic gates and as well. In this step, tool also performs the logic optimization, which means removing all the unwanted wires, cells, flip-flops with constant logic 0 or logic 1. So here additionally tool performs another step, which is, as I said, logic optimization, which means it removes all the unwanted cells or wires. So that does comes under the optimization stage, which we can say in the generic mapping. And the next stage is technology mapping. So in technology mapping, what that it do is after getting the gated level netlist, which is in the gates, which are in the form of generic gates. So in this step, the tool maps the generic gates into the technology file as whatever the technology node we are working, those technology file will be provided. According to that, it will be. Hello, 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 Rajat. Okay. Thank you. So in technology mapping, what it does means, so it maps the generic gate level netlist to the technology file, which we are giving according to the technology which we are working. So what it will do means, it will apply those particular timing or power or area constraints will be present in this particular lib file. So according to that, the gated level generic netlist will be mapped to the technology wise, which means nothing but it will apply some constraints to the generic gate level netlist in the technology mapping stage. So moving to the next stage, optimization. So after the technology mapping, optimization stage will be there in this synthesis flow. So here what that tool will do means, okay. So during this step, tool optimize the design. So after mapping and again, it will perform some another stage. This means nothing but optimization. So after getting all the gated level netlist, so here it will see some, there is possibility to do any optimization. Like let's say for example, changing of VT cells. In our circuit, we have combination cells in the data path, right? So in the data path, the cells which we are having, like let's say like AND gate, OR gate, or NAND, NOR, AOA, OA cells. So all these kind of cells will be in the combinational circuit, like likewise. So it will be a changing of the VT cells or changing those particular cells of the drive chain or the logic restructuring, cloning, adding repeaters, and the buffering. So all these steps will be performed in the optimization to get a better optimized netlist in terms of like to meet the design constraints. In our VLSI design, what are the constraints which we have means mainly we focus on three things. One is area, another one is timing, another one is power. So in order to meet all these three constraints, we need these are the techniques which apply in the optimization stage. So next stage is DFT, which means design for test. So what we will do in this DFT stage means, it helps us to detect manufacturing defects in the design. Let's say if we have any cells or flops, so it may have manufactured defects. So DFT team will be separately will be there. They insert some extra hardware logics, will be provided some files. So upon taking those files, when we are using those files, we can with that we can check whether any manufacturing defects have been present in our design or not. With that we can see. So DFT engineers works on instancing extra hardware blocks as part of the design itself for increasing the testability of the chips. And the next one is DFT team will insert scan chains to the design, which means adding extra input and enable pin to the flops. These are used to check whether or not by giving test inputs during testing. Yes, which means DFT team will additional will also provide scan chains, which means it will test whether any manufacturing defects are there or not. Means with the help of scan chains it will test. So let's say if we have some scan chain ports will be there, some six ports are there, means one is three ports are input ports, another three ports are output ports, means it will decide based on that complexity of the design. It will be equally divided those scan chain lengths, and then whenever the input will be provided to the scan chain input port, within this much of time that output should be come. Likewise, some expectations will be there according to that how much time it is taking to pass those inputs to the output ports to the these kind of flops. With this, we come to know that all the flops in our design are working fine. And the next step is incremental optimization. So incremental optimization means already we have gone one optimization. So after performing DFT, again one more optimization will be there. So that's why we are calling it as an incremental optimization. Okay. So in this stage, one more round of optimization will happen. And it uses same optimization techniques as discussed above. So what are the techniques we are discussed above? Like changing of VT cells, changing drive strength of the cells, logic restructuring, and adding repeaters, cloning and buffering. All these techniques will be applied again further to get a better optimized netlist. So here we may get doubt like what is like a cloning or a buffering, like I say. Like cloning means if we have some AND gate cell is there. So according it has to drive some load. Let's say it is having fan out of 10. So the same kind of duplicate cell will be there like AND gate replica, so that it can be used to split that load equally. Likewise, the techniques which we provide for the optimization is called as a cloning here. So optimization is completed. So coming to the next stage, outputs. So once after optimization and all everything is done, we have to dump the outputs. What are the all outputs will get means first one is optimized gate level netlist. This is the foremost main. The other one is SDC. The next one is CANDEF. And the reports. Reports means which were also QR reports, which we can say area, power, timing, and all. So these are all the outputs which we dump after completing this logic synthesis. Now coming to now we'll go for the physical aware synthesis. So physical aware synthesis means it is a bit advanced compared to the logic synthesis. So what are the major difference between the logic synthesis and physical aware synthesis? We are all have some kind of doubt like that. So basically the small difference is in the physical aware synthesis, the tool places all the standard cells in the core area, when it is not happen in the logic synthesis. That is a major difference between the logic synthesis and physical aware synthesis. Okay. And here also the whatever the logic synthesis steps and all it perform, the same steps will be there to meet the constraints and the requirements of like in the design area, power, and timing. So as I said, physical aware synthesis of flow is also same as a logical synthesis, but some additional add-ons will be there in terms of like we'll see in the input files and the generating output. So now compared to the logic synthesis, there we have the wire load model synthesis. This method is more accurate where we are using the physical aware synthesis. If you use physical aware synthesis, the timing finding of before and after actual placement would be more closely related to one another, which means like the major issue which we face is like fixing the timing and area utilization, power. So these are all the major concerns for a chip to design. So in the physical aware synthesis, it is very accurate to determine all these things and it is easy to fix those things. We'll discuss physical aware synthesis flow also. Now, so in flow, this is the first is inputs. So what are the inputs which we provide in this physical aware synthesis is RTL, physical libraries, which means lib and left timing library. And one more is MC file. Another one is STC file. The other one is the cap tables or QRC text files. And the other one is floor plan def. It is an optional. And the other one is UPF. So next coming to the is steps. What are the steps it will performs in the physical aware synthesis? Which means in the first step, it performs the importing the input files. So what are all the inputs we have discussed earlier? So those files should be imported using these commands. We can import all the input files, set underscore db dot lib or dot left likewise. And the next step is you have to read the HDL and elaborate, which means like whatever the inputs which we have provided, it will be read all those files and it will perform the elaborate stage. Like as we discussed it earlier in logic synthesis flow. For this, the command is read underscore HDL. And the next step is read HDC, which means the command is read underscore HDC. So in this step, as usual, in logic synthesis, how the timing constraints and design constraints have been given in HDC file, those all the constraints will be read and it will be applied to the design. And the next step is sanity checks. For this, again, the commands are same, like check underscore design, check underscore timing. And the next step is generic mapping. So in generic mapping, the command is syn underscore generic. The mapping will be done here. The next step is technology mapping. For this, the command is syn underscore map. After technology mapping, again the optimization. So the optimization for that command is syn underscore opto. Again, after that, generating outputs. So for that outputs, what we have to generate means for that we have to write underscore HDC to dump the HDC output, and as well as Verilog netlist file means write underscore HDL, and as well generating reports. The reports means QR reports, report area, report timing, report power. So these are all under the steps in the physical level synthesis. And the outputs, as we discussed, the outputs are gate level netlist and HDC file, scan-def, reports, placed def file, TripleMC file. Now we'll see the PNR flow. So basically overview of the PNR flow is this is the one. So we have like inputs HDC, UPF, scan-def, def, libs, and tech. So after this, the flow actually it starts from the import design, floor plan, placement, place of CTS, CTS of route of chip finish, like fill and finish will be done here, and followed by sign off. So all these flow stages will be discussed one by one in the floor plan. So for the floor plan, what are the inputs which we are providing means one is a netlist. After synthesis, whatever the outputs which we are getting, that outputs will be taken as an inputs for this the floor plan. That is a netlist. And another is technology file, TechLef, TripleMC file. In TripleMC file, what other we are having is a .lib, RC coefficient files, HDC, .hdc, synopsis design constraint file, physical library, which means .lef, and the TLU plus and UPF. After taking all the inputs, we have to perform again some sanity checks, and again we'll go for the floor plan. So basically, what is floor plan? What we will do in the floor plan? Floor plan is nothing but if we are in this floor plan stage, it is the basic stage of the PNR flow, which means here we will create the core area and we'll specify the pin where it should be aligned in which side based on the hierarchy, based on architecture level and whatever the guidelines comes from the top level people. Likewise, we'll arrange that IO pins, and after that we'll arrange the macros based on the macro guidelines. We'll place the macros, and after that, if required any additional placement blockages means we'll place all those blockages in the core area, which is the basic start of the PNR flow. In floor plan, we have two types of designs. One is core limited and another is pad limited. We'll discuss this one. So core limited design. So core limited design means what it means. This is the core area, which we are seeing in the white color. So this is the core area. And this is the core IO boundary, where it is showing this one. And outside to that, this is the IO filler pads. These are the IO pads, IO filler pads, which we can say. On the corners which we are having pads, those are called as a corner pads. Core limited design is very simple. Like if the core area is more, like it is more dominated, let's say if the outside of the IO filler pads are very less, which means we can say it is a core limited design. So here the core area will be a more compared to the IO filler pads. And coming to the pad limited design. So the pad limited design is the size of the die is restricted by the pad area. Core area is dominated by the pad area. So here what it will do means whatever the sorry. Okay, the voice is clear. Okay. So here, as we seen earlier, the IO filler pads which are sitting outside is very less. Now it is very more here. So that everything is same, but here more IO pads are there. With this, we can say it is a pad limited design. So basically, these are the two types of designs which we see in the PNR flow. And the next one is floor plan control parameters. So in the floor plan, what are the parameters it will control? Like to estimate the core size means how we will estimate means the taking of the standard cell area plus macro area plus blockages area divided by standard cell utilization. Upon taking all these values, we'll get that core size, how much the core size is taking and all. Now the next one is aspect ratio. So aspect ratio, we can calculate it based on the height of the core area and the width of the core area by taking the ratio of these two things, or horizontal routing tracks or vertical routing tracks. Any of the thing is fine. With this, we can determine that aspect ratio of the our block. If it is equal, one means the block will be looks like a square. If it is less than one means it's like somewhat lengthwise it will be less, and if it is greater than one means some widthwise it will be more. Likewise, that the block shapes will be vary. And the next one is routing tracks. So we see that there are more routing tracks in our design. Generally, we say. So what is a routing tracks in generally? Why do we require? How it will be taken? So it means in our design we have metal information from the tech left, which means metal layer information. So from there, this metal layer is divided into number of horizontal, vertical, and horizontal lines. So these lines can be considered as a routing track. Okay. So these tracks are virtual actually. So upon on these tracks only the metals will be lay, which means they align exactly center to the track, and the center of the one track to the center of the another track, which we call it as a pitch. It is a major component factor in the tech left, and we get this value from the tech left. With this, these tracks will be aligned properly, and these tracks are virtual created for routing purpose. A net or route middle is exactly aligned automatically to the routing track as shown in the below picture. So as shown in this figure, how this metal track is like metal layer is being aligned on this particular middle means exactly it will be aligned middle to the routing track here. This is the routing track. As we discussed, this is the height and this is the width. If these two things are equal means the block will be looks like a square. And moving to the next slide. Under macro guidelines. So after deciding the core size, the core shape, and placing all the IO pins, well, we in the design we have macros means we have certain guidelines to place all the macros. So we have to follow those guidelines while placing the macros. The guidelines are first thing, macros should be placed across the boundary, and the macros should be color by based on the hierarchy level. We have to give the color for those macros. After that, we will place the macros across the boundary. In that macros which are communicating to the ports, which for those macros we'll place near to the ports. And the next thing is macro to standard cell communication. Likewise, we will arrange the macros. And the next step is macro to macro communication. So by checking all these three things, we'll arrange the macros across the boundary. And after that, macro pins should be always placed towards the core area, which means core center area. It should be C to which means why? Because means to connect the standard cells pins properly. And we should not place the macros in the middle. If we place the macros in the middle of the core area, we are wasting unnecessary area, which means we can say like if one flop is sitting here, another one flop is sitting here. For these two flops, the routing should be done means it will take this path. So this is very long and it will reflects in the bad routing and the timing and power. So congestion, all this will be triggered again. So we should not place the macros in the core area. Avoid notches in the core area. Notches means whenever we place the macros across the boundary, we should not leave any spaces in between these two macros likewise. If these two macros don't have any pins means we can abort, like how this A and B is aborted. Likewise, we can abort. If not means it will be a notch issue. While placing the standard cells, again, it will create some congestion issues. Avoid crisscross. So crisscross means while placing the macro to macro, so macro to macro communication we will see. So there should be a linear, it has to be linear communication. It should not be like this communication. If you see means this is the crisscross connection. It should not be present like this. Place talking macros near to each other. So what are the macros are talking to each other? We should place those two macros one each other. Like if it will be two side of the macros should not having any pins means we can abort those one. If they are having some pins, let's say if A and B macros are having some pins and C is having some pins. So those two are communicating means we have to leave some channel space in between them in order to align like one set of power like VDD and VSS should follow in this channel place. So that's why we are leaving this channel space here. So and the last step is maintain proper halo around the macro. So around the macro, we have to maintain some proper halo area, which means some kind of partial blockage, and we can place around the macros. So and the next is types of floor plan. So we can do floor plan in three different styles. One is abutted, and another is non-abutted, and another one is mixed. In abutted, what it means in the top level we have plenty of blocks. Let's say we are having some 6 blocks. So if all the 6 blocks are combined, like there is no space in between each of these 2 blocks, any block in the abutted design, which means it is called as an abutted. And the same non-abutted means we leave some channel space between block to block and every block to block, means non-abutted type of floor plan. And the mixed means a combination of abutted and non-abutted, which means blocks or 3 blocks may abutted and the rest of the blocks maybe leave some channel space. So that will be called as a mixed. This type of floor plans are there. For our designs while running the flow, it will be get the information from the top level people. Moving to the next stage, outputs. So once after doing all the floor plan, we will dump the outputs. What are on the outputs we will dump is floor plan depth and the macro placing and information will be there. Core boundary and area, pin positions, placement and routing blockages positions will be present. So all these outputs have to be dumped up once completing the floor plan. Now moving to the power plan. So in power plan, what are all the inputs you are giving? Netlist.v, SDC, physical and logical libraries, TLU plus UPF. So these are all the input files which we are giving to the power plant stage as we discussed earlier. Almost same inputs. Here we are getting some UPF, which means power information related will be present in this file. Like if we creation of a VDD VSS nets and supply to those particular VDD VSS nets, and any multi-voltage designs or any multi-power designs means it will be all the information will be present in the UPF file. So how the power distribution will be done in our designs. So actually what the power team will be doing means we have to understand the basic core area and this is the die area. As we discussed earlier, these are the IO filler pads. From here we have VDD pad. So from here the VDD, the black color is VSS pad and here the red color is VDD pad. So from the here the VDD pad to it will go to here, which we called as a trunk. So from the trunk to again where it is going to, that means it is going to the power stripes here. So power stripes are here black and red. So again from there it will go to the power rails or S roads. So from there it will go to the standard cells. Likewise the power distribution will be done. Like we can see here in this figure also, from power pads to power rings, and these power rings to power stripes, and from these power stripes to power rails, and from power rails to standard cells. So this is the structure, how the power will be distributed in the levels wise. This is the 3D structure. With this we can easily understand. This is the top power layer, top metal layer. These are the stripes VDD and VSS. From here it will be followed like this. This is the VSS and this one is the VDD power wire. So likewise wires will be followed here from top level to bottom layer. This is the base layer, and let's say M0 like that. These are the power rails, VSS and VDD. So for this, the connections will be done in this way in the 3D structure. So these are the few commands during the power plant stage we are using. So to create the power rings and the stripes, we use add ring and add stripe. And for the S route, we give the command S route. And for the global net connections based on the pin type VDD or VSS, we'll give this type of global net connections. And for the cells which were connecting tie high and tie low pins, for that we'll use this command like tie high pin VDD to instance and tie low means pin VSS to hyphen instance. After this, we have to verify the connectivity of the PG net which we created. For that, we use this command verify PG connectivity. And after the check PG DRC. What it does means any power related DRC errors means like any power shorts or power opens or there means will be reported over here upon giving the command. So upon clearing all these things, we'll come to know that it is having power done correctly. If you are having any multi-voltage area designs means, we can give this command, create a voltage area hyphen power domains. Whatever the domains we are having with that according to the block name and the region where which we want to create here in some power area. So this is the one region and this is the one region means will be given that coordinates likewise and hyphen target utilization. So these are all the comments which we given in the power planning stage. And the outputs. So after the power distribution, what on the outputs will give floor plan def and with power distribution network, which means PDN. Now moving to the placement stage. So in placement, the inputs are not netlist B, HDC, physical and logical libraries, TLU plus UPF, and additional floor plan def will be provided here. So checks before placement. So before starting the placement, we need to do some checks. What are and all checks means the netlist should be clean. And the other one is proper pin placement. The pins should be placed properly. And the macros pre-placed cells are fixed. After doing the macro placement, we have to fix those macros. And the pre-physical cells are there also means it has to be fixed. So it has to check whether it is fixed or not. Likewise, we have to see. And the power rush should be free DRCs. Like earlier, as we discussed, after giving the check PG DRC, if you are reporting any PG shorts or PG opens means we can see power routes should be free from those kind of shorts and opens. Placement strategies. So in placement, what are the strategies it will take or it will follow means based majorly three strategies. One is timing driven placement, another one is congestion driven, another one is area driven. So these are all the major three strategies which will happen in the placement during the placement. Placement stages. So in placement, it will do in different stages wise. Let's say one is a course placement, another one is a detail placement, another one is optimization. So in course placement, again, it will have some steps. What are the steps it will have means like first it will tool will place all the standard cells roughly on the core area based on the hierarchy. And after that, the nets which are having fan outs high means for those nets, it will do buffering. That will is called as a high fan out net synthesis. And after that, it performs scan chain reordering. So in this step, what the tool it does means, let's say if we are having some group of flops, around 10 flops are there. If the first flop is connected to the ninth flop, and the ninth flop is connected to the second flop. So if such kind of connections are there means the tool will arrange all the flops in a series order. Likewise, in such a way, first flop is connected to the second, and the second one will be connected to the third. Third will be followed by four. Likewise, it will be connected up to the 10 flops to pass the scan chains and all. The next step is logical optimization. So tool performs the optimization based on the logic whatever we are having in this stage, which means the tool it performs taken by the Boolean algebra expressions. With that, it will reduce the logic further if any possible are having a, like it will take some K maps or to reduce that logic and all. So it will optimize the gated level netlist. Let's say, for example, wherever it is having some 4 cells or 5 cells instead of 1 or 2. Likewise, it will optimize all the cells like BT swapping, sizing, buffering. Whether it required here buffer means it will place that buffer. If it not, it will remove all those buffers. Cloning, logic restructuring. So all these steps will be performed in the logic optimization. Once after finishing all these steps, it will go for the detailed placement stage. In this stage, it will be do again in the 3 steps. One is area, congestion, and timing. So here, detail placement means the tool place the standard cells which are placed. It will be assigned guidelines to the site row and according to the core area, whatever the site rows we have been provided. So it will be aligned legally in this stage. So once after the standard cells are placed legally, it will be based on that how much that area it is going to utilize it in the earlier course placement stage. Now it will be taken into a area utilization. So based on the area driven placement stage, as we discussed earlier, it will be taken all the flops which were communicating near to that in order to reduce the congestion and the timing to get a better timing and all. Based on all those algorithms, the tool performs again one more placement iterations in the number of phase. In each phase, it will have some number of iterations. Ultimately, that placement will be done in the detailed placement stage. So once after placing all the standard cells legally and in a less amount of area and in a better in terms of congestion and timing, it will go for the optimization. Here again, tool performs another round of optimization in order to optimize the DRV and setup timing. So DRV means, as we know, max strength, max cap, and max vanout. So it will optimize all these three things. And after that, setup timing. So for timing wise, it will improve the setup, because in placement stage we have only setup. Since clock is ideal, the clock race didn't build, so we'll check only for setup here in this stage. So it will optimize these DRVs and setup timing. And moving to the next stage, congestion. So as we discussed in the placement stage, the major issues which we face here is congestion and timing. So congestion, what is congestion? Congestion means whenever we have any routing resources is very less than the required, then the congestion will occur. So as I said here, the number of available routing resources is less than the required. If the available is, like, let's say for example 10, but the requirement is 20, so there will cause some lack of some routing resources. So then the tool, how it will performs means, the tool will breaks the entire core area into small cells, which we call as a G cells. Whenever it has to connect to the standard cells, it will be use some routing resources, right? So these routing resources, whenever in that particular G cell area, it is expecting some three layers, means it is having only one. So in that case, it will report some horizontal resources are very less compared to the vertical. Likewise, that congestion will be occurring. So what are the reasons? Let's see. Reasons are like high standard cell density in a small area. Like all the standard cells are placed in a certain small area, means there it causes congestion. Placement of standard cells near the macros. If more number of cells are placed near the macro or around the macro, means it will cause congestion, because they have some connections, and again they have, for while doing routing, it will cause again congestion. So and again, the macro corner areas, there if any OAI cells have been placed, means for this kind of special cells it have more pins, so it will cause more pin density. So that is also one kind of reason for congestion. Another one is bad floor plan, which means we not placing macros properly, or no proper blockages have been given, or halos are not provided properly, means it will also cause a congestion. So and the next one is placing macros at the center instead of the boundary. As we discussed it earlier, macros if we place around the boundary, if not, nothing will happen. If we place in the center, means it will cause congestion. And the next one is during IO optimization, tool does buffering. So lot of cells placed in the core area. As we discussed it earlier, that detail placement and course placement, it will perform some optimization. So while doing optimization, it adds some extra cells, like nothing but buffers. Okay, sorry. Any doubt? Okay. So while it adds some buffers, means, so there are lot of cells in our core area. So it also may cause congestion, and also it also cause power issue. So these are and all the reasons for congestion. So how we have to fix if we see some congestion, means we'll discuss. Sorry. So congestion fixes techniques. How we will fix a congestion means, these are the commands which we can fix. Let's say set underscore congestion underscore options hyphen max utilization. The number which we are providing, it depends on the block to block and our the design complexity wise. I am providing here 0.45 means 45%, and hyphen coordinates x1, y1, x2, y2 coordinates, which means it will create one area in that it is, we are saying that to the tool, use this amount of area till the utilization number which we are given here. So up to maximum it will utilize this area in the coordinates which we have given. So in that in that particular area, congestion gets some free. And the other one is place of hyphen congestion driven effort high. We have to make sure that congestion driven effort should be high. So then only the congestion count will be very less. This is the one of the technique. The another one technique is we can provide the blockages to reduce the congestion. We have generally three types of blockages. One is a soft, hard, and partial. So based on the requirement of the design at the time of to resolve the congestion, we use according to that. So here, if you want to use some blockage, means the command is create underscore placement underscore blockage hyphen boundary. The coordinates which were where we want a boundary, like where we want the blockages and all, we'll give those kind of coordinates here. And after hyphen type partial, if you want to use partial means hyphen type partial. So partial means we have to give some blocked percentage or yellow percentage. We have to mention either one of these two. So I'm mentioning here blocked percentage 40, which means in that particular blockage area I'm blocking 40%. So allowable is only 60%. So 60% of cells only will be placed in that blockage area. So, and the next one is create keyboard margin, hyphen type soft. So here, this is for like if you are having more pin congestion, like congestion due to pin density. In that cases, we use keyboard margin commands, like it's nothing but cell padding. Like we are mentioning here, the coordinates hyphen outer, followed by the coordinates my underscore lib underscore macro around that. Next, change the floor plan, macro placement, macro spacing, and pin orientation. Still, after all the using these techniques, we are seeing congestion means we need to check for the macro placement. If possible, we have to go for another iteration. And reorder, still if it is having some congestion means the other step is reordering the scan chains to reduce the congestion. And the next one is timing. So after fixing that congestion, the other issue in the setup, like in the placement stage, we are seeing is timing, that to particularly setup. So here we are focused only on setup because the clock is ideal. So while fixing the setup, how we will fix means if the timing path in that we'll have data path and the clock path. If the data path is very much is there, like data path depth is very there means we can see like that the logic depth is more. So we can provide some extra cycle to capture data properly. So for that cases, we'll give the set multi-cycle path command, hyphen setup 3, hyphen from the register to register, hyphen do that one. And if the data path is a logic depth is less, if it is having any possible to optimize means like changing the driving strength, less changing of VT swapping, like this data path optimization, it will be a benefit for us in fixing the setup timing. So in the data path, we have to make sure have better drive strength cells in the data path and set timing optimization effort level to high. So likewise, as we discussed it for congestion, for timing optimization also effort should be high. Then only the timing will be get better optimized. The other technique which we use generally is group paths. So what are all the paths are violating within timing violations in the setup window. So we have path groups like let's say reg to reg, into reg, reg to out, and into out. So according to that, which are on the paths are being violating, we'll take those particular start point and end point common to that. Either one of the start or end points are common means we'll provide particular paths to that paths. We provide some weightage. We can change that weightage according to our iterations with getting better results or not, and followed by hyphen priority 100. 100 means whatever the path we are mentioning here in this command, it will tool, we are saying explicitly to the tool, take this as a highest priority for this path to get a better timing. So that is the command which we are using for path group. And the next one is create bound. In our design, if we are not having any timing, like any congestion related issues are not there, but still we are seeing some timing issues. Likewise means we can create bounds for that particular scenario where a group of cells will be placed in one particular bound according near to that area. Here also again we have three types. One is soft, another one is hard, another one is exclusive. So based on the situation where they're in the design, we use according to that one, and followed by the boundary that are coordinates and the instance one. And the next one is set false path. If in our design we are not, so let's say if start point is getting one clock and capturing path is getting another clock, and still those two clocks are asynchronous, like they're not syncing any point of time. By taking the LCM of those two clock periods, then if we get some LCM is good. If not, it is not matching means then we can term it as a false path. So for those kind of particular paths, we can give set false path commands. And still, if you are not seeing any timing issues in for into reg or reg to out, like that means if there is a possibility for moving the ports near to the register means we can move the ports. So that is the port movement which we do in the placement stage. If still the timing is more issues in the design means there is a one more technique to reduce the timing is magnet placement. So in magnet placement, what it does means we'll tell the tool some are the fixed objects. Let's say some macros are the fixed objects means So according to that, which are on the standard cell logic communicates to that macro cells, it will be arranged properly according to that communication to the macro to standard cell. So for that we'll get some better timing. That is the one of the technique to better the timing. So these are all the techniques to better the timing in the placement stage. Moving to the next stage, checks after placement. Once after placement is done, we need to check for the things. The first one is legalization. Check legality will be the command. So with that command, we'll see any legality issues are there. Means in some cases, some cells will be overlapped. Some cells are not aligned properly to the site rows. Likewise, it will be reported in the legalization. And check PG connections for all the cells or for all the standard cells, how the PG connections have been there, and have to be checked according to that one. And we have to check the congestion and timing as we seen earlier. For the congestion, report underscore congestion, and timing, report underscore timing. If any congestion related, timing related errors means, it will be popped out here. And check whether all don't touch cells and nets are preserved. So in placement stage, by synthesis team itself, they provide some don't touch cells or don't touch nets by default. Whether these are preserved or not, whether it is using or not, we have to check that one also. If any don't touch cell is coming into the like in the timing path and it is having means, we have to check that one whether it is having don't touch or don't nets or like cells or nets according to that. And next, check the total utilization of design after placement. So once after placement is done, we have to check the utilization. This is a major factor, because utilization, if it is more means further, if you are going to the further stages, it will be more complex and very difficult to resolve those issues. So as much as possible to better utilize the design means, we can do anything in the placement in the stage only. By let's say in one of the situation where I faced is like more number of utilization number is there. So once after checking and all like that, I came to know that it is the register optimization is got disabled. After that, I enabled means I got some better utilization. And the next one is outputs. So what are the outputs which we get means placement def. In that def, we have the information of cell location, cell PG connections and all, etc. Congestion report, timing report, and utilization. Now moving to the next stage, CTS. So in CTS, the inputs are placement def and the target latency and skew, which means in the SDC. And the next one is the spec file. In this file, we have clock buffers, clock inverters, clock cells information. And along with that, we have max strand, max cap, max fan out information. And along with that, NDR rules mainly. These all the information will be present in the spec file. And the routing materials also, which we have to use for the clocks, and all those information will be presented here in the spec file. Now moving to the next stage. So in CTS, what is our target or goal? Means we have to make sure that skew, insertion delay, max strand, max cap, max fan out. So these are all the major things we have to see in the CTS stage. Issues. So in CTS, what are the issues we see generally means skew or latency related issue. It is not meeting to the target latency or target skew means it will be an issue for us. And the timing, congestion, min pulse width violations, DRV violations, crosstalk. So these are the main issues which we see in the CTS. So latency. Once after generally clock tree is built from the clock source, which is a phase locked loop, like a PLL oscillator to the clock pin of the flop. So once the clock tree is built, the clock is taking the time to come from the PLL to the sync pin of the flop means that is called as a latency. It is divided into two types. One is source latency, another is network. The amount of time it is taking from PLL to clock defined in our block, the clock port. So there it is called as a source latency. From there again, the clock port to the clock pin of the flop, how much amount of time it is taking, it is called as a network latency. The next one is a skew. What is skew? Skew is generally whenever after getting the clock from the clock port, once the clock is going to the one flop here, flip-flop 1, the same clock is going to the flip-flop 2. It is traveling some extra distance. compared to the flip-flop 1. So there will be some amount of time interval differences will be there in between these two flops of getting the clock. That difference which we called as a skew. We can see in the waveform here. So the clock which is getting to the flip-flop 1, this is the waveform. And the clock which is getting to the flip-flop, it is getting delayed from the 1ns. So the amount of time it is taking difference between this capture flop and the launch flop is called as a skew. In this scenario, 1ns is the skew between the capture flop and launch flop. So if we are having any skew issue, which means or as a latency issue in our design means, we can fix with this the command set clock balance points -clock, the clocks which are getting the clock, and -delay, the value which amount of clock we have to delay that value. And after that, -balance points, clock pin, -scenario, all scenarios. With this command, we can fix that any skew related issues or latency related issues means we can fix the issues. So let's say set clock latency is also one more command. Whatever the value which was based on the timing report, or how much value we are given here means to get a better timing means we will provide that value based on the calculations. After that, get clocks and a clock name. So this is the clock pull. And coming to the clock push. So how we'll do clock push means we'll add some buffers either to the for setup fixing we'll add buffers to the capture path, and if it is hold means we'll add the buffers to the launch path. Likewise, we will do the clock push, which means we'll insert some buffers that instant name and the clock pin, that particular flop of the clock pin, the library name, lip cell, what are the new cell which we want to add, that one, new cell name, new net name. So with this command, we can do the clock push to fix the issues of like latency or skew, which we encountered in the CTS stage. Now moving to the other stage, timing. So in CTS, as we discussed, timing is also one of the major factors which we have to look on. So this is the general, we use the command report timing -net, trend, cap, max paths, the no split, max delay or min delay based on the setup or hold. If it is max delay, it means it is the setup. And if it is a min delay means it is the hold. So once after giving the command, we'll get the timing report. After analyzing the timing report, whether the timing report, the one which we get is a valid or not means by verifying the start point and end point, the clocks are getting properly or not. Likewise. So if we have in the timing, we have any uncertainty issues means based on the setup or hold, that values will be provided according to the clocks. So to fix the uncertainty issues in the timing. Still we have some hold issues. For that, in CTS stage, we use mostly app options to fix the hold. So in general, what are the app options means? We have used different types of app options I have listed here. You can see here, like while building the clock tree for the clock optimized during the clock optimization, we have to check whether this hold effort is a value high or less. Likewise, we have to provide this one. And about the CCD timing and route of flow, CCD value, all these app option values, how default it is set, whether it is a true or false, whether it is low or high. Likewise, certain app options will be there. According to that, we have to set to the high or true. After fixing the timing and all, we will check one more violation here is min pulse width violation. Min pulse width violation, why it causes, which means in general, while building the clock tree, we use mostly clock cells, which has clock buffer or clock inverter. In general, it will have equal rise and equal fall times. But in some cases, whenever it has some unequal rise and unequal fall delay means with these combination cells, the data might not be captured properly to the flops. So it may enter into the metastable state. So ultimately, the timing will get cause failure over here. So we have to check that amount of width that we are getting is as expected as minimum width is getting or not. Like the command we are using is report underscore timing -check type pulse underscore width. So after giving this command, we'll see whether any pulse width violations are there or not. If it is there means we have to fix. How we will fix means set underscore min underscore pulse underscore width -high. The width is like if it is level 1, which means high. So how much amount of it we are expecting, like that value will be given. Get clocks, the clock which for that clock will be given here. And if we are seeing low level, which means level 0, logic 0. So for that, we'll give -low, the value which we want to give low to get to resolve the min pulse width value. That value will be provided here, followed by get clocks. So these are the fixes for the min pulse width violation. Now moving to the next stage, DRVs. So to check whether DRVs have been any violation means, this is the command report underscore constraints all underscore violators. So with this command, we can say that if in our design any DRV like max tran and max cap issues, it will be reported over here. So if max tran issue is there, let's say net length is more. If in my design, if the timing path, the net length is very some 100 or 300 microns is there means, then we can add the buffers to break the net delay. So then the tran will be fixed. If the net length is very small, like let's say 1 micron or 2 micron, but still we are seeing some tran violation means either we have to do driver cell, have to upsize that driver cell, or the receiver cell which is getting that violation, that receiver cell we have to downsize that one. Else, if still it is not fixing means if possibility of checking the VT swapping likewise. And here I want to add one more point, like in the max cap issue also, if the fan out is more, likewise means we can split the fan out by the command which we are given below here. Split fan out lip cell, the cell name driver, the driver which we have been got the cap issue, that pin we will be providing here, and the driver which is driving those many loads will be given here loads. Those loads pins will be provided here. New cell name, new net name. So the cell which we are adding will be seen as some new cell name to identify for us easy understanding. In some cases, even after splitting the fan out, we'll see some max cap or max fan out issues. So in that cases, what we have to do is the cell which we are adding for splitting the fan out, the cell we can do upsize. Okay. So like I mentioned here, in some cases, the newly manually added buffer can upsize if still the issue is seen. So I have faced such kind of issues. So I have just added here for better understanding. In some cases, after giving this command also, we won't see that fixing of the cap or fan out issue. Then we can upsize the driver cell, which we added manually. Then it can see the resolving of the max cap issue. Now moving to the next stage, crosstalk. So here, what is crosstalk generally? Crosstalk means whenever any unwanted signal capacitance is developing between the two nets, it is called as a crosstalk. It means it is interfering with the one net. It means communicating between two nets, which is not expected. So what it causes means some signal distortion or delay or any voltage related issues. Likewise, it will be causing. So if we see any crosstalk issues means how we will fix. Major fixes for the crosstalk are by providing the shielding. Like whether on the nets which we are seeing the crosstalk, either it is a clock net or a victim net. Now on which net we are seeing that crosstalk means around that net we'll provide the buffering on the constant nets, and we provide the spacing between aggressor net and victim net. So whenever we increasing the spacing, so that amount of coupling capacitance will be effect will be very less. Victim net width increasing, then resistance decrease is used at routing also. So whenever we have some victim nets, if that victim net will be increased, it means then it will have some switching activity will be better. So the crosstalk will be less for in that cases also. On the aggressor nets, which we are seeing crosstalk, those nets will be connected to the ground and victim net to the voltage discharge. So that there will be a, this is called as a shielding, which means providing the constant 0 and constant 1 nets to the victim and aggressor. We have to make sure to maintain the stable supply in order to not get the crosstalk effect. And fast slew rate. So fast slew rate means the transition from 0 to 1, the slew which is, it should be very fast. So then it will be switching activities also will be very good. Jogging, increase of track by half inch. Like if you are seeing still the crosstalk issue means we can do jog means the jogging means like we are chopping the metal layer to another metal layer likewise. And layer jumping. Jumping layer means we can switch to the higher metal layer. If we will have some higher uh, like low resistance and more width, so that it will have a better switching current activity in that cell. And the other fixes are like the aggressor net which is driving that net, the cell should be downsized, or else the cell which is driving the victim net, that cell should be upsized, vice versa, like that. And deep and well, guard rings. So these are all the fixes for the crosstalk. Now checks. So once after doing the CTS and all, we have to check for the timing, utilization, congestion, skew, and insertion delay or meeting or not. All cells should be legalized. So these checks has to be must and should have to do after the CTS. Now moving to the route. So for the route, the inputs are same like previous netlist and CTS database, timing and physical libraries, tech left, cap tables or QRC text file, SDC. So in routing, we are providing additional QRC text file where you are having some RC coefficients. Checks. So in routing stage, we have to check whether any geometry issues, timing related like setup or hold are triggering or not, any utilization, any legalization, congestion, all these checks has to be done in the routing stage itself. Goals. So in routing, what are our goals to maintain is minimize the total interconnect or wire length and wires. While after doing the routing, which means it for connecting the standard cells to the power rails and to the ports which we are communicating according to that. It has to maintain the total interconnect of wire length should be minimum. Complete the routing within the area of the design. So whatever the area it is left for the routing, it should be done in that particular area only. So it will be our goal actually. So in that case, that area also, utilization also will be a better. No DRC violations. We have to make sure that any DRC violation should not be triggered in the routing stage. As I said earlier, timing also should be clean and no LVS. You have to check this one also, layout versus schematic, which we can see here, shorts and opens. Shorts and opens, if any floating routes or any there is, it will be reported over here. These are the few commands which we use in the routing stage. Route design. Once after giving this command, it will do routing. The routing also will be done in two stages. One is trial route, another one is global route. So in trial route, it will just estimate, it will first see whether any routing is possible to the shortest distance likewise. And after again, the track will be get aligned, and detailed routing, it will do actual routing to the standard cells. And the next stage is after design. So for the design or routing stage, this is the command. After design, hyphen post route. And we are seeing some issues in the routing stage, which means some timing issues, means like any optimization which we can do in the data path, means for that scenario, we can do size cell or else VT swapping or changing the drive strength and all. The next one is set routing rule hyphen max routing layer. We have to mention the routing layers, like how much till the routing should be done, till how much the metal layers it can be used for routing. Like this, it has to be mentioned here. So once any manual fixes for doing for the timing, we have to do the route ECO. So for the cells which we added manually, for those cells, we have to do ECO manually, means we have to use this command route underscore ECO. And still, if you are having any max fan out issue or any load issues, like I said earlier, split fan out will be a command. This is the command for splitting the fan out to reduce the max cap or max fan out issues. And these are the outputs. So here the outputs are GDS file, timing and congestion report, SPEF, DEF, and HTC. So these are the outputs which will be dumped after the once the routing stage will be completed. Once it will be completed means we'll provide the database to the sign-off team, which means PV team will be provided to the database. Yes, that's it. Thank you for all. If anyone having any doubts, means you can ask me. Hello. Hello.
Anyone have any doubt? Anyone? Lakshmi, Anusha,
Yeah, if anyone have any doubt means you can ask me.
Satish. Okay, so I guess we can end the session. Okay, fine. So thank you so much, sir. Thank you, everyone. Thank you.
Yeah, okay, Rajat. Thank you, Rajat.
Okay.
Thank you.